So thank you very much, everybody, for coming to our Innovative Discovery series. Despite we are the first day of the spring, but it's snowing. I guess it's the first spring seminar. We really have a treat today. Dr. Trabulsi from University of Delaware is here. Before I introduce her, I just want to remind a few housekeeping steps. So online participants, please keep mics muted unless asking questions. We welcome questions. Use chat feature in BlueJeans if you have technological questions. For everybody, all the previous presentations are available on our website, DE-CTR.org. If you want to get a CME credit, please sign in. We can receive credit online, but must use BlueJeans chat to contact Sarah Kay at start of presentation. So everybody who is online and wants credit, please contact Sarah Kay. And finally, next week, we also have another nutrition-related talk, obesity and the food environment among minority groups from Mia Papas. So as I said, we are delighted to have Dr. Trabulsi here today. Dr. Trabulsi is assistant professor at University of Delaware in the Department of Behavioral Health and Nutrition. She has a PhD from University of Wisconsin-Madison and did a postdoc at CHOP in Philadelphia. She has also some industry experience. She was associate director of research in Pfizer, in the nutrition department of Pfizer. She is a PI or co-PI on multiple R01 grants and has a long list of publications, and we are very excited to have you here today with us.
Thank you for having me. And please, I welcome questions. I'm glad for this to be interactive, so if you have questions as we go along, please feel free to ask them. So I just wanted to start by acknowledging some of my collaborators. Dr. Julie Manella. Okay, so Dr. Julie Manella is a biopsychologist at Monell Chemical Senses Center. That's in Philadelphia. It's loosely affiliated with the University of Pennsylvania, and she is the co-PI on one of the grants with me. Mia Papas and I from the University of Delaware also work closely together. At Children's Hospital of Philadelphia, Virginia Stallings and Joan Shaw. At University of Pennsylvania, Sharon Irving, Barbara Madoff-Cooper, and Gary Wu. And then I am still in touch with my mentor at the University of Wisconsin, and that's Dale Scheller and Tim Schreiber. I thought I'd start today with just some background. I'll give you just a general overview of my research interests and some of the projects that I'm involved with. I do want to talk a little bit about method, or some of the methods I use, because that will help you understand the presentation. And then I'll dive into three of my current studies. I don't think I need to do this background, but I am a graduate. My undergraduate degree is from the University of Delaware. I am a registered dietitian. I did work clinically. You can now figure out my age. I think I should have taken the dates off the slide. I did work clinically at Children's Hospital of Philadelphia for 6 years, loved it, rotated through most every floor in that department, but really had a good experience there. Did my graduate work at University of Wisconsin in Madison. If anybody's ever been to the near the Midwest, stop by Madison. It's really a great town, lots of lakes everywhere. I then went back to CHOP for my postdoctoral training. I did some time in industry doing global infant nutrition studies, maternal studies, infant nutrition as well. And then in 2010, I started at the University of Delaware. And really my focus ever since I've been there is to start to develop this research program in energy balance, in obesity, and then in maternal and infant nutrition. Those are my global interests. In terms of my funded studies, I'll be telling you about the first one, the impact of diet composition on energy balance, satiety, and growth in a little bit. We were fortunate enough to get awarded a supplement for that, so I was able to bring on additional graduate students to the project. We definitely needed that. We have about 90 subject visits a week at times in Philadelphia, and things were getting busy. I'm glad to say we are done enrollment, and so now our subject visits are going down. I'm also going to be collaborating with Allison Carpin. She's got an R01 looking at does a supermarket improve the diet and food environment of low-income residents. And then I'm collaborating with Michael Vest. We've got a project going energy balance and clinical outcomes of obese mechanically ventilated patients in the ICU. Finishing up some earlier work, so I'll be talking with you today about growth and energy expenditure in children that have been infants with congenital heart disease. I'm working with Mia Pappas on a study of nutrition and activity among Hispanic mothers and their children, and we've got a paper going out on that. Just starting a paper looking at total energy expenditure in children with Down syndromes with colleagues at Children's Hospital in Philadelphia. And then I'll tell you about, this is just a small pilot study that we're doing. It's infant feeding and biomarkers of satiation and satiety in healthy term infants. And so I'm currently enrolling in that study, and we're hoping to turn that one into our next grant. And my collaborator is Julie Manella. Okay. Just to give you a little bit of background on methods, I measure total energy expenditure a lot. And in order to do that, we use a method called the doubly labeled water method. And basically, this is a stable isotope method that we use to measure total energy expenditure. So we get resting, we get it when you're sleeping, when you're going to work, activities of daily living. It is your total energy expenditure. It uses stable isotopes. And so this is just a reminder that this is not a radioactive method. These are stable isotopes. When you learned about hydrogen and oxygen in chemistry class, you learned hydrogen with a mass number of 1, oxygen with a mass number of 16, and that's because 99% of oxygen is oxygen 16, and 99% of hydrogen in our environment is H1. However, we do have deuterium and tripodium, and then we have oxygen 17 and oxygen 18. They're just present in much smaller quantities. So what the doubly labeled water method does is it takes tap water, you distill off the lighter isotopes. So the oxygen 16 comes off and the hydrogen 1 comes off, and what you have left is oxygen 17 and 18, and then deuterium and H3. And so that's what the method takes advantage of. You dose individuals with oxygen 18 and deuterium. So it's water with enriched quantities of those stable isotopes. And when you have that water, you can use it as a metabolic tracer. So the oxygen 18 is eliminated as carbon dioxide in water, so you get the slope of the elimination curve. The deuterium is just lost as water, and if you subtract this equation from that equation, you get carbon dioxide production. Once you have carbon dioxide production, you can calculate O2 consumption, and once you have that, you can calculate total energy expenditure. So that's the theory of it. Here's how it works in practice. You collect either a urine sample or a blood sample from individuals prior to dosing them, because you need to know how much oxygen 18 and deuterium they naturally have in their body. Then you dose them with this water that is enriched with these two isotopes, and you collect 2 urine samples at 3 and 4 hours afterwards. Then that individual can go on their merry way for 7 to 14 days, depending on how much dose you've given them. They can go to work, they can work out, everything that they typically do. They come back 7 to 14 days later, you collect 2 more urine or blood samples, and from there you can measure the abundance of those isotopes and how they've eliminated from the body over time. And that's how you calculate energy expenditure. So the beautiful thing about the doubly labeled water method, it is considered the gold standard for the measurement of total energy expenditure, because you're capturing people when they rest, when they go about their activities of daily living, work, exercise. You get multiple days of measurement. You can calculate their energy expenditure over 7 to 14 days. The other way we can measure total energy expenditure is in a metabolic chamber. But the limitations of this is these rooms are typically about the size of an elevator or 2 times the size of an elevator. And subjects go in it, they seal it, they measure O2 consumption, CO2 production while the subject's in there. But as you can see, it's a really small room. So you can capture rest, you can put an exercise bike in there and capture exercise, but you're not really capturing them getting in their car, going to work, walking to the mall, and everything else that they typically do in a given day. So that's why the doubly labeled water method is considered our gold standard. The other thing that I do a lot is I assess diet, and there are lots of researchers out there that assess diet. There are some that focus at the group level. We have researchers at the USDA that basically look at it in terms of food balance. How many heads of cattle did we start with in the U.S. at the beginning of the year versus the end of the year? And they'll calculate beef consumption from that. There are researchers that look at universal product codes. So, every time you go through the grocery store and they scan that, they can get that data and think about what are we consuming as a nation. Some people look at it at the household level. They can use something called a food account method, where you go into the home, you take an inventory of everything that's in there at the beginning of the week, you come back a week later and you see what's left there. I tend to look at it at the individual level because then I can then aggregate the data and also look at it at the group level. So there's many different ways that we can assess diet at the individual level. We have 24-hour recalls. We have food records where the participant writes everything down, food frequency questionnaires, and something called a diet history technique, which isn't really used that much anymore. I'm often asked to collaborate on studies of diets, and people will say to me, well, I want to use the best method. What's the best method out there? And the answer is there isn't one. The most important thing that it depends on is the nutrient that you're interested in. Some methods are better for macronutrients. Some methods are better for micronutrients. So you start with asking, what's your outcome? What are you interested in? And then you can work backwards. You can think about the setting they're in. I talked about the nutrients of interest. What are the characteristics of the population? What can they handle? And what might they not be able to handle? And then, of course, everything comes down to resources and time and money. Once you collect information about diet, you then sometimes want to convert it right into nutrient intake. What's their omega-3 intake? What's their saturated fatty acid intake? And I typically use Nutrition Data System for Research. It's NDSR, as this is considered one of the most comprehensive commercial systems out there. So if you're not doing research with the USDA, this is what most researchers and academic institutions use to take food data and then calculate it into nutrient intake data. It's pretty expensive to buy and to maintain, but it is one of the most comprehensive systems out there, so that's why we all use it. Okay, so those are basically the methods that I use. And so what I'll start to do is I'll start off with my larger study, which is diet composition in infancy and its effects on growth in healthy infants. So I don't think that I need to share all of this with you. We know that there's an obesity epidemic here in the U.S. It's not just adults, it's also in our children, and it's even making its way down to infancy. So we know that overweight and obesity in childhood has important implications for both current health issues as well as later. Children who are overweight or obese are at higher risk for CVD, diabetes. They can have orthopedic issues, depression, and then they're more likely to become overweight or obese adults. And the prevalence in the United States in terms of in the pediatric population is about a quarter of 2 to 5-year-olds, and about a third or so of 6 to 11 and 12 to 19-year-olds are overweight or obese. The CDC recently looked at data on infants, so children less than 2 years of age, and they define it differently. You're not obese as an infant, but you're defined as overweight if you are greater than or equal to the 95th percentile of weight for recumbent length on your sex-specific growth chart. So as you can see, if you look at all the data, in terms of children less than 2 years of age, it's somewhere around 8 to 10% are defined as having high weight for their length. And if you want to think of that another way, that's like a BMI, but it's for a baby. So these are the growth charts, and this is how we typically monitor infant growth, right? All of you are clinicians, or you've seen this in your own children. So we monitor weight, length, and head circumference as markers of overall health. We use these growth charts. It's a series of these percentile lines. This is the age on the bottom. This is the weight. This is the length. The 5th percentile up to the 95th percentile, right? And we plot them over time to make sure that they're growing well. So as healthcare providers, we use growth charts, but as researchers, we're going to try to figure out whether one group differs from another group, and we can't just use these percentile lines. So what we use are z-scores, and that's what we use to communicate growth differences between groups. So a z-score is used to compare the growth of one group to a reference group. The z-score represents the deviation of the study group mean from your reference group mean. And basically, nearly all infants in a population should fall somewhere between a z-score of -2 and +2. So the way that I like to explain it to people is if you go back to your growth chart, because that's what makes sense to most of us, a z-score of -2 for your weight for age is about the 5th percentile. A z-score of 0 for your weight for age is the 50th, so that's average. And then if your z-score is +2, then it's the 95th percentile. And it's the same for the length, and then the same for the weight for length. So if I tell you someone has a z-score of +2 for their weight for length, that means they're at the 95th percentile of their weight for length. If the z-score is -2, that's going to be a thinner child, right? They're going to be at about the 5th percentile in terms of their weight for length. Okay. So we have a lot of studies that have been developing over the last year that show evidence that weight status and weight gain in infancy affects later life weight status. And so I only put a handful of studies up there, but people have looked at your weight for length Z-score at 6 months. They've looked at whether you gain weight rapidly from 0 to 4 months. They've looked at, again, this is a weight gain study, and then weight gain. And then they've looked at, so how quickly do you grow in the first 6 months of life? And then what's your obesity risk at 3 years of age, 7, 17, or 20? And the take home is that all of these studies show that the faster you grow, the higher your weight gain in the first 6 months of life, the greater the likelihood for childhood and adulthood overweight. So this was the Tavares study. This is done in Boston. You have quartiles of weight for length, so that's almost like a BMI. On this axis, you have quartile of weight for length at birth on this axis. So basically, the heavier you are at birth, the higher your weight for length, the greater your probability of being overweight at 3. The higher your weight for length at 6 months, so this is the highest one, the higher the probability. And then what you really don't want to be is you don't want to be in the highest at birth and the highest at 6 months, because then there's your probability of being overweight at 3 years of age. It gets higher. This was really one of the first studies. This is a really large data set, like 19,000 individuals. This is weight gain in the first 4 months of life. This is your birth weight. So again, you can see if you're in the highest birth weight category, you have a higher probability. This is overweight at 7. Here's your weight gain categories. If you're in the highest category of weight gain, there's your probability. And then if you're in both, your probability of being overweight at 7 is even higher. This was a study that was done, I believe it's done in Sweden, and this looked at rapid growth. So they looked at changes in Z-scores. So if your Z-score for your weight went up by greater than 0.67 in the first 6 months of life, you were defined as a rapid grower. If your Z-score increased by less than 0.67 Z-scores, then you were considered a normal grower. And what we see is, here's the kids that are rapid growers. They gain weight quickly, and then they maintain that higher BMI through 7 years of age. Whereas kids that are growing more slowly, or the normal growers, they maintain a lower BMI through 7 years of age. So once you put it on, it seems like you're maintaining it over time, or certainly into childhood. And then this was another study that looked at rapid increases. Again, these are changes in the weight Z-score. Here's whether you were rapid between 0 and 6 months, and this is whether you were rapid between 3 years of age and 6 years of age. And however you parse the data, when you gain weight rapidly, your BMI is higher, and these were outcomes at 17 years of age. So no matter how they define rapid growth, whether it's by grams per day that they're gaining or changes in Z-scores, we're consistently seeing that those that grow rapidly or at the highest rate tend to be at increased rates for obesity. So that's what we have here. Early growth, rapid gain, or large changes in weight for length affect later life weight status. But what we also know is that diet composition can really affect how infants grow in those first 6 months of life. So one of the biggest differentiators, right, in diet when it comes to infant, because the liquid really is their only source of nutrition for at least 4 months, is whether they're fed human milk or whether they're fed infant formula. We know that human milk is our preferred source of nutrition for infants, and if you can breastfeed, you should. However, if an infant cannot be breastfed, infant formula is considered the next best feeding alternative. In terms of human milk, it's under homeostatic control in terms of its nutrient content. Our major and our trace minerals in human milk are not substantially affected by maternal diet, with the 2 exceptions being selenium and iodine. So if mom's diet is deficient in those, the milk will also be. Maternal vitamin intake doesn't really have a large role in terms of what the vitamin content of the milk will be, with the exceptions being D and K, because they're not always provided in sufficient quantity in human milk. Lipids are the most variable constituents, and mom's diet does play a role. Both her short-term and her long-term diet can affect the fatty acid composition of human milk. The composition of human milk is also very variable depending on the stage of lactation. So how many days postpartum is mom? The protein content of the milk changes over time. So this was a study that I did when I was with Wyeth Nutrition. And this was a study of over 270 moms, so about 30 moms in 9 different countries across the globe. They collected human milk samples. And so down here you have days of lactation or days postpartum, and then you have the amount of protein in the human milk in terms of grams per liter. And so what we see here is we know that early on human milk is really rich in protein, and over time human milk goes down. So here at about 3 months, the total protein concentration of human milk is about 12 grams per liter. But really, from about day 100 on, it's all the way down at about 10 grams per liter in terms of total protein. When we look at our standard formulas, and these are formulas across the globe, not just here in the US, most standard formulas have about 13 to 14 grams per liter. What else do you notice about this, about the total protein that the baby gets from infant formula? It's constant, right? So about here, formula-fed babies are getting about the same protein as human milk-fed infants, but out here, their protein intake is consistently higher. So why is it so high? Well, human milk is made for human babies, and so the essential amino acid pattern in human milk is perfected for the infant. Most formulas are made from cow's milk, so the essential amino acids are specific for the cow, not necessarily for human infants. So what happens is the amino acid composition of cow's milk is just different. It tends to be a lot lower in tyrosine and cysteine, and it's a lot higher in lysine and threonine. So what companies have to do is they have to provide higher total protein content so the infant gets all of the essential amino acids it needs from the milk. So that's why infant formulas are always a little bit higher in total protein, because the cow's milk is limiting in some of the essential amino acids human infants need. So they just raise total protein so those levels of essential amino acids meet the needs of the human infant. The alternative for a formula company is to provide the same amount of protein as cow's milk, but then they'd have to add back some essential amino acids. And that's cost, and that's also a source of contamination. So they're not so keen on doing it. They're starting to do it. Formula companies are starting to try to mimic human milk and lower the total protein and try to only have to add back 1 or 2. But they can't get it much lower than it currently is without having to add back a lot more. So what's the consequence of this higher protein? And that's led to the protein hypothesis. We know that babies that are fed formula tend to grow faster. They tend to be rapid gainers. They tend to be about 1 pound heavier at the end of the first year of life compared to a breastfed infant. That doesn't sound like a big deal, but if you're only 20 pounds, 1 pound is a big deal. So the protein hypothesis says that infants that are fed formula take in protein in excess of their needs. That leads to excess concentrations of circulating amino acids, especially those that are insulin, that cause increases in insulin. So this increased concentration of circulating amino acids leads to higher insulin and IGF-1 concentrations, which leads to increased weight gain and higher weight for length in infancy, which could put them at long-term risk for obesity. So this was really one of our first studies that showed the phenomenon that breastfed babies grow differently than formula-fed babies. This is that weight for length Z-score, right? So this is almost like a measure of BMI. This is a 50th percentile. And what we see is everybody kind of starts out the same, right? And then somewhere around 3 months of age, we see that the formula-fed kids have this higher weight for length Z-score, and the breastfed infants are leaner through 24 months of age. And so this study has shown it, and numerous studies have shown it since then. This is just a list of a few of the studies that showed that formula-fed infants are larger than breastfed infants by the end of the first year of life. And there's probably about 10 more that I could have listed on here. So we have this body of literature that says early diet affects growth, right? Formula-fed infants tend to be growing more rapidly than breastfed. And then we've got a ton of literature that says if you gain rapidly, if you have greater weight for length in infancy, you're at greater risk for it later in life. We think, or it's been thought, that the total protein of the diet has something to do with it. However, we're also learning that that might not be the full story. It might not just be the total protein that these infants are receiving when they're formula fed. It could be the form of the protein in the diet that's also important. So these are a bunch of common infant formulas that are out there. As I mentioned, most are cow's milk formula, so these are just two different brands. These are intact proteins. 90% of infants in the U.S. get these types of formulas. More recently, and I would say in the last 5 or 6 years, there's been this new category in infant formula. They're called partial protein hydrolysate formulas. So they hydrolyze that intact protein down to small peptides. This product has been out on the market forever, and others like it. This is extensive protein hydrolysate formula. They've taken the proteins, they hydrolyze them down to very, very small peptides, and in fact, most of the formula is free amino acids. And they've done this to reduce the allergenicity of cow's milk. So children that are allergic to cow's milk formula, they'll put them on this formula because it's hypoallergenic. It leads to less reaction to the cow's milk protein in the formula because everything's in the form of a free amino acid rather than this complex protein. So this study was published in 2011, and so I had been at UD for about a year when it was published. And what they found was that when they took infants and they fed them that hydrolyzed protein formula, those small amino acids and really small peptides, they had growth parameters, weight for age and weight for length, that followed the WHO growth standards, which are based on breastfed infants. So here's a group of formula-fed kids that grew like the breastfed infant, not like a cow's milk-fed infant. Those infants that were randomized to cow's milk had this accelerated growth pattern. By 8 months, they had a significantly higher weight for length compared to the kids that were randomized to that protein hydrolysate formula. So these were the data. They were healthy term infants, and at 0.5 months of age, they either got the protein hydrolysate or the cow's milk formula. These are weight for age, weight for length, and this is length for age. And what you can see is that these are the kids that are fed the cow's milk formula. And you can see that their weight for length and their weight for age is significantly higher than the kids that got the protein hydrolysate formula. So that was our first clue that maybe it's not total protein, it could be the form of it. Yes?
Sorry for interruption. Couldn't read from here. The age, how far it goes?
This is going to 7.5 months.
Only months. There is no further study like teenager age.
No, but so we do have those other studies, right, that say if you gain earlier, right, if you gain rapidly, if you are in the highest weight for length category at 6 months of age, you're at greater risk for being in the highest at 3, 7, 17, and 20.
Years old. And then those studies, including breastfed baby and also formula fed baby.
Exactly. So rapid growth, whether you're breastfed or formula fed, rapid growth, excessive weight gain in early infancy seems to place you at higher risk for overweight and obesity later in life, whether you look at 3 years of age, 7, 17, 20, no matter where you put that cutoff.
Is there any study that, I'm sure there are, but what the data look like for the two groups, infant with breastfed babies, the growth between age and then time, the weight and time, and also the formula-fed babies, the growth between age and then the weight?
Lots of studies that show that breastfeeding has a protective effect on later life weight status. So it does protect you. You're at decreased risk for obesity if you've been breastfed. Even when you account for socioeconomic status, maternal BMI, paternal BMI. So what could be happening? Why are these babies that get this protein hydrolysate formula growing differently? And so that's where my brain starts to take off because I've studied energy balance for most of my career. So when I think of energy balance, I think of what are you burning? Are you losing any? Like, are you malabsorbing any? And then what's your intake? And we know that if these two sides are in balance, a person is weight stable. If your intake is greater, then you're going to gain weight. If your intake is less than your output, you're going to lose weight. So that's your positive energy balance and your negative energy balance. So in adults who are weight stable, your energy expenditure is equal to your energy intake, or that's the basic equation there. In kids, they do need to take about 1 to 2% more energy than they burn in order for age-appropriate growth to occur. So it's not a perfect equation, but it's close to a perfect equation. So going back to that study that showed that those kids grew differently, that was done by Julie Manella. She posited she questioned in the article, well, how come they grew differently? Did they perhaps burn more calories? Is there something about this formula, something about getting these small peptides and free amino acids that stimulated energy expenditure? But she didn't really measure it in that study, and I couldn't find any studies that have looked at that. Could it be that there were differences in intake? Well, she did capture that. Moms kept records at home just on the number of feedings a day. And then each time they came to the lab monthly, she would do a feeding in the lab, and she would weigh the bottle before and weigh the bottle after, and she would capture it. So what she did find is the number of feedings a day didn't differ between the groups, but the intake volume when she did that in-lab feeding was different every time that she did it. It seemed like when the kids got the EPHF formula, they drank a little bit less each time. So here are the data. There's no differences in the number of feedings between the CMF group and the PHF group, the protein hydrolysate, but there is a difference in the amount of each feeding. They're taking somewhere between 15 mLs and 45 mLs less each time that they feed the formula. So you can imagine over 7 feedings a day, that adds up to a lot. So when you go back and you look at the literature about this protein hydrolysate formula, lots of people have been studying it in terms of allergy risk. So here, this is a family history of allergy. They would randomize kids with a family history of allergy to cow's milk formula or this protein hydrolysate formula, and they would look at allergy later in life. Was it protective? Turns out it is. It seems to be somewhat protective in them developing allergies later in life. But we started to dig into these papers, and if you read some of the results, they'll mention things like CMF infants exhibited greater BMI change than did EPHF infants between 2 and 12 months. EPHF fed infants consumed less formula than did CMF infants fed the cow's milk formula. So throughout several of these papers, they're mentioning slower growth and less intake with feedings when kids are put on this formula. It could be that perhaps they lost more energy in their stool. However, when Julie Manella did that study, she didn't measure that. So all you have to go on is perhaps it's energy intake, and that's why those kids grow like a breastfed infant, and they didn't have that accelerated growth. So I contacted Julie Manella after reading this. She didn't know me from Adam. And I said, I read your paper in pediatrics, and I do energy balance and diet for a living. So I've got this great idea for a study. So she invited me to the Monell Center, which is on Penn's campus, and I pitched this idea. We're going to do it again. We're going to have a bigger group, and we're going to measure it by doubly labeled water, and we're going to collect these diet records at home. And so I probably spewed everything out in about 30 minutes flat, and I could see she was processing, and then I just didn't hear from her for a week, and I thought, oh, well. And then she called me, and she's like, let's talk again. And so sure enough, I've been going to the Monell Center now every Monday for the last 4 years, and we've got this great collaboration going. So I'm very grateful to her for not thinking I was a crazy person and trusting me a little bit. So this is my large-scale study that's in Philadelphia. It's 144 formula-fed infants. Just like her study, we randomized them to the cow's milk formula or the protein hydrolysate. We are going to follow them for 18 months. They come into the study when they're relatively young. We do not approach any baby that's breastfed or receiving breast milk or infant formula. We do not want to deter moms from breastfeeding. So if they're breastfeeding at all, even one feeding a day, we will not approach them for the study. They have to be formula feeding only for at least 3 days before we will even approach them to join the study. So we're measuring energy balance, we're measuring growth, and eventually we're going to measure gut microbiota because we're really interested in what are these free amino acids and these peptides doing to the gut microbiota. Okay, so they come in when they're about 2 weeks of age, and we had huge energy balance measures done at baseline. Then they get randomized to one of the 2 formulas. We do this huge battery of energy balance at 3 months, and then again at 12 months, and then we keep following growth out to 18 months. So we're doing total energy expenditure by doubly labeled water. They go to CHOP for a resting energy expenditure. We do weighed energy intake for 3 days. So we send them home with 36 pre-made bottles, basically. We tell mom, feed as much as you normally want to. When you're done that bottle, put it in the dirty bottle bag. We weigh the bottle before, and we weigh the bottle after. So we have weighed intake for 3 days. And then we also have energy loss in stool. So moms collect all the stools for 3 days. They freeze them, and then we send them out for analysis. We are doing monthly measures of growth. We do that in laboratory feeding session. We get a stool sample each month for the gut microbiota, and we ask tons of feeding questionnaire studies. So this was the study where I said sometimes we're up to 90 study visits a week because they're coming back so often and they have lots of samples. All the samples come to my lab. So my graduate students love, we've processed thousands of urine and stool samples. They're loving it, loving it. So our primary aim is to characterize the effect of diet on energy expenditure. We want to know what the effect of diet composition is on energy intake and then energy loss. Those are our primary aims. We're also looking at feeding behaviors. Kids that get fed this protein hydrolysate formula because the amino acids tend to be bitter. Julie Manella has noticed that they tend to like vegetables a little bit more later in life because maybe they experience that bitter taste a little bit earlier. So we're looking at feeding dynamics and intake over days. We're looking at taste-related genes, and we're collecting those monthly stool samples. And then we're also going to keep following their growth out to 18 months of age rather than stopping it at 7.5 months of age. So sadly, I have no results for you, just we have completed enrollment. We did not get to 144. We're exhausted and we're out of money at 141. So we're like, that's good enough. And we are just now really in massive data sample processing, basically, in order to determine their total energy expenditure, the energy loss in stool, and we're doing lots of diet records. So that's where we are. Our database will be unblinded. Last subject will be done the study, or at least the 12 months of the study, in February of next year, and then I get to play with the data. So I'm very, very excited. Okay, so why do I care so much about formula-fed infants? And this is the reason that I care so much. It'd be great if everybody could breastfeed. This is the reality here in the U.S. This is in hospital. I don't know if you can see this yellow, but everywhere from here up, all that yellow that I put in, these are babies that are either getting solely formula or a mix of formula and breast milk. So you can see it's about 50% in the hospital. By 4 months of age, 60% of infants are getting formula in combination with breast milk or as their sole source. And then it just keeps getting higher. So down here, these are the only infants exclusively breastfed still. When you're out here at about 12 months of age, 90% of babies in the U.S. are being exposed to formula. So if the cow's milk formula is not the ideal formula, that would be really good if we could figure out something that's a little bit better for them. That led me to this next study that I'm doing, and I have some graduate students. So Julie and I are collaborating on this, and then my graduate student Lindsay's on this study. We are trying to look at biomarkers of satiation and satiety. So satiation is what makes you stop eating, right? All of you came in, you had a lovely lunch, and you eventually said, that's enough. I'm done eating. I'm not going to continue eating. That's what satiation is. Satiety is how long you go between meals. So if we go back to Julie's original study, there was no difference in satiety. They ate the same number of times a day. But babies fed that protein hydrolysate formula satiate early. They drink, and they send those signals from their gut to their brain that says, I'm done. It's time to start eating. So they satiate early. So what we'd like to do is develop a model system to determine what makes them satiate earlier. So we're experimentally evaluating both at the group level and the individual level differences in satiation in response to diets of different composition. So we're basically looking at these biomarkers when we feed infants either cow's milk or protein hydrolysate formula. So as I mentioned, energy intake is really regulated by this complex system that we have between the gut and the brain. We have peptides that are released from our gut when we eat, right, that eventually get to our bloodstream, go to the hypothalamus that tell us that food is on board and it's time to stop eating. We've got peripheral signals, and then we've got these adiposity signals that relay information about our body fat stores to our brain. So these are things like leptin, and these are things I'll be talking about. This is GLP-1, GIP, and things like that. So glucagon-like peptide, GLP-1, peptide tyrosine, that's PYY, you've all heard of that, and gastric inhibitory peptide. These are things that start low when we start a meal, and they go up over time. When they go up, we start to decrease our intake. Right? Those are the signals that go to the brain. So GLP, PYY, and GIP all go up when you eat. Ghrelin, this is that satiety one I was telling you about. Over time, so I eat my breakfast, my ghrelin's going up, 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 and then I eat my lunch and it plummets down. And then it goes up, 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 up. So ghrelin rises, and when it peaks, it tells you to eat. and then as it starts to come back, as soon as you eat, it starts to come back down. So this ghrelin tells you how many times a day to eat. These ones tell you when to stop basically eating your meal. So when we do these feeding studies in the lab, what I'm expecting, so we take blood before the feeding and we take blood after the feeding. These are babies. I just do a little heel stick. I've got a little capillary tube so I can collect it. I take a ml of blood. That's it. And we do put EMLA on them so they don't really feel much. So what I expect is that GIP, PYY, GLP are going to start low. They're going to be they get randomized to get cow's milk formula or EPH formula on different days. I expect these ones to go up after the feeding, and I expect ghrelin to come down after the infant is fed. These are these adiposity signals. They do interact with those peptides that I was talking about, and they can either render the peptide more effective or less effective depending on how much body fat stores you have, basically. So my primary aim is to investigate differences in the gut peptide response to diets of different compositions in formula-fed infants, and then I really wanted to, again, see if I can replicate that volume finding. So it's a within and between subject study. Infants come to the lab twice, and the study visits are about 2 to 5 days apart. During each visit, the formula-fed infant is provided with either a cow's milk formula or EPH. They get it in counterbalanced order. We measure the amount of formula they consume, and then we look at these biomarkers before and after the feeding. We also have a breastfed arm in our study as a reference group. Our hypotheses are here. We think that infants when they get EPHF, they're going to have higher concentrations of these satiation peptides. Maybe that's why they're drinking less. We think they're going to drink less formula when they get EPHF, and that there's going to be a inverse relationship between energy intake and the concentrations of these satiation peptides. So to date, we just did baby 11 this morning. So I'll show you data on 12 babies. So basically, in terms of age, we're getting babies that are about 80 to 90 days old in the study. These are my formula-fed. These are the breastfed infants. Moms tend to be about 28 or 30 years of age, and about a third of them are first-time mothers. In terms of volume, we're starting to see it. Our babies that get the EPHF formula are drinking about 140 mLs per feeding, whereas babies that get cow's milk are drinking about 156. So we're starting to see differences in that. Even if you divide volume by kilogram of body weight, we're still seeing that they're drinking more when they get the cow's milk fed formula in the lab. I will also say that the feeding, when they take the EPHF, that protein hydrolysate, they feed slowly. It's like a slower feed. Whereas when they get the cow's milk, they just gulp it down. Not sure what that is yet. I would need more babies to try to think about that.
So this is also a randomized trial?
I wouldn't say. So I'm blinded. My graduate students are doing this. I've just seen the data, but they're coming in counterbalanced order. So some baby 1 gets cow's milk their first day. Baby 2 might get EPHF. We've got a randomized order for when they're coming in. This is data on formula-fed infants. This is the data on the breastfed infants. Now keep in mind, this is 4 babies. This is 6, right? So this is really, really small sample size. This is my PYY. This is before feeding and after feeding, before and after. And what I can basically say is I haven't run a lot of stats. There's 6 babies on my top graph, and there's 4 babies down here. So I'm just really, really reluctant to say anything or even think anything at this time. What it is showing me is, A, we can collect the blood, we can analyze and get these peptides out of only a ml of blood, so it's not a lot once you spin it down to serum. Just like we thought for PYY, this is before the meal, and then after the meal, everybody's going up, with the exception of one baby over here that's breastfed. For some reason, they're going down. But that's the PYY. Here's the GLP-1, and again, so most people go up. I expect all of these things to go up and tell the brain it's time to stop eating. So everybody's kind of going up, but a couple kids are going down, so I didn't expect that. This is the one that I was like, oh, when I saw the graph, I was like, oh, put it away. Like, I don't want to see it. This is ghrelin, right? So I told you ghrelin should be high when you're hungry, and then you eat, and it should go down. So here's my ghrelin, and, breastfed and formula-fed and breastfed, I've got kids going every which way. So I'm going to say more to come. And, maybe when we have 20 babies in this study, this will, those will just be outliers, and it'll start to make more sense.
Are the mothers instructed to come in for the lab visit, like when the baby's hungry?
Yes. Yep. So we tell them to come in after, we don't want to tell her when to feed, you know what I mean? But yes. And most babies are, believe it or not, on a similar schedule. Maybe we as parents put them on that schedule. But, most babies are coming into the lab around 9, and then they're hanging out for maybe an hour or so until we start to see them sucking on their finger and get fussy. We want them to get a little fussy, but not too fussy, right? We don't want them in that exasperated state when they're feeding.
How did you enroll these babies?
So I have, believe it or not, Craigslist is a source of a source of, that's been my most successful. Word of mouth has been very successful. Also, there's I'm going to butcher the name of it. It's the Parents Baby Express. It's like Parents First or something. So out of the University of Delaware Cooperative Extension, there's a Healthy Baby, Healthy Beginnings or something. Some newsletter that, thank you, some of you are making me feel better. It's a newsletter that goes out to new moms. And so we put our feeding pamphlet in there. And that has been successful. So between that newsletter that goes monthly to new moms in Newcastle County and Craigslist, and all the ad says for Craigslist is infant feeding study at the University of Delaware. That's all it says. We've been able to get about, 2 babies a month, 3 babies a month. There's lots of different ways that you can recruit for these studies, but this has been a fine pace for me for now with everything else going on.
All they got is to go to your lab, get the baby fed, and then go home.
Mm-hmm.
Nothing else. Mm-hmm. You don't send them more bottles or more formula.
No, I'm really interested in like a laboratory feeding study. What happens under my control conditions? What I've really found from this is that babies are taking all different times to feed, right? And that's going to affect the change in the gut peptide. They also are drinking all different amounts. So my goal is to get enough pilot data to write a grant, and what I'd like to do is feed them a fixed volume. What happens when they get 60 mLs of CMF? And what happens when they get 60 mLs of the EPHF? What happens to these gut peptides? So for now, because everybody's very variable in the amount they drink.
Yeah. And they only come once?
They come twice. So one day they'll get the CMF formula, and the next day they'll get the EPHF, or vice versa. But that way it can be a within as well as a between subject design.
And you don't control other food. You don't control other intake.
They have to be between 30 and 90 days old and not consuming any solid foods yet. So most babies are not fed solid foods between 30 and 90 days. I will say that the average age of food consumption, for some infants, around 4 months is when you'll see a lot of infants, regardless of the American Academy of Pediatric recommendations. A lot of moms start feeding at 4 months.
So timing isn't something you record here.
We do. We measure what time the feeding starts, what time it ends, the volume, the time of the blood draw. Everything gets documented in terms of time.
So there's a variable amount of leptin and ghrelin that's present in breast milk, but it's destroyed in the processing of formula. So you're measuring the concentration that's in the breast milk?
I've collected the breast milk samples. I don't have the finances at the moment, but they're all in my -80 freezer. Yeah. There's also apparently, bovine, in infant formula, there's bovine ghrelin, and they're studying whether it's, having an effect, but there is some evidence that even formula-fed babies are getting ghrelin, but it's bovine form.
They don't get leptin.
But they get the ghrelin. Yeah. Actually, leptin has been found too in human milk.
No, it's in, we did the study here.
Oh, okay. You're saying in the infant formula.
Yeah.
Yeah. Okay, so where I'm going with this is just more and more babies, and I see that I'm running out of time. I'll be really fast, as if I haven't been speaking fast enough. So, growth and energy expenditure in infants with congenital heart disease. Just a little bit of background. Congenital heart defects affect about 8 out of 1,000 newborns. Some of them are just simple. Some of them are really complex disorders that require a lot of medical and surgical care. The treatment has gotten much better, so these infants are really surviving in a lot higher rates, and most of them are leading very active and productive adult lives. One of the issues is that some of the kids, especially with the more complex defects, are just not growing. As you can imagine, about 50% of infants with CHD exhibit poor growth, 30% fall below the 3rd percentile in their weight for age early in infancy. That can affect both their later life growth as well as neurodevelopmental outcomes later in life. It can affect wound healing at the time they're in the surgery. Lots of reasons why poor growth is not considered a good thing. So it's thought that it's very multifactorial, but it's likely due to problems with energy intake and total energy expenditure. And really the mantra has been that their heart is so, the physiology is so not normal, that it's likely leading to stress or leading to increased energy expenditure. And that has really been the mantra for a very, very long time. So this was a study that was being done when I was a postdoc at CHOP. So I was doing all the doubly labeled water, basically. They wanted to measure total energy expenditure in these kids with pretty bad defects, basically. That was the goal. So kids with CHD were recruited from the cardiac intensive care unit at CHOP. We had healthy infants from the community. Everybody had to have been full term with no other anomalies present, basically. If you were a kid with CHD, you had to have had your surgical intervention within the first 30 days of life to get into the study. So they measured anthropometric measures. They got birth weight from the medical chart, but then they measured everything at study visits. Weight, length, and head circumference were done at baseline, 3 months and 12 months. And then we converted everything into those growth Z-scores. And then total energy expenditure was measured at 3 months and 12 months post their surgical intervention. And that was done in both the kids with CHD and in the healthy controls. So in terms of the types of defects that these kids had, hypoplastic left heart was common, as well as transposition of the great arteries and tetralogy of Fallot. For those of you that are not familiar, I'm not going to go through this in detail. This is hypoplastic left heart. So this is a normal heart. This is the hypoplastic left heart. So you can see the structures on this side are very, very underdeveloped. You see this hypertrophied wall here. So basically, you have issues with the left ventricle, the mitral valve, the aortic valve, as well as the ascending portion of the aorta. And basically, the left side of the heart can't pump enough oxygen-rich blood to the body. So they go in there and they surgically correct it. That's several surgeries to get the heart as functional as possible. And I say surgical intervention because for some kids, it's never a correction, right? If you have this, you can't really correct that much. So they just make it as the best physiology as they can. Transposition of the great arteries, basically the two main arteries carrying blood out of the heart. So you've got the main pulmonary artery and the aorta are switched or transposed. So the problem is you've got oxygen poor blood coming in from the body and it's pumped, it doesn't go to the heart, it's basically pumped directly out to the rest of the body. You've got oxygen rich blood from the lungs that enters the heart and it's pumped right back into the lungs because those two are switched. So that's the issue with that transposition. And then you have tetralogy of Fallot, which is really a series of 4 defects. You have a ventral septal defect, so a hole between the right and the left ventricle, pulmonary stenosis, issues with the aortic valve, and you have right ventricle hypertrophy. So basically, again, you've got oxygen poor blood being distributed to the body. So these are major malformations in terms of the structure. So in this study, we ended up with 24 healthy infants. We had 26 infants with CHD, and there weren't really any demographic differences between these groups. That's the take-home of this slide. We had 8 kids that at the end, after surgery, had single ventricle physiology, so they really didn't have a 4-chamber heart, and then the remainder of the kids had biventricular physiology. So these are the data at 3 months of age, and I was just going to point out the weight for length Z-score. So here's the healthy term infants. We had 12 at 3 months of age. The weight for length is negative 0.34 in our healthy kids, but in our CHD kids, it's negative 0.75. That was not statistically significantly different, but it basically says these kids are lighter. They weigh less for how long they are compared to our healthy control kids. And then at 12 months, the kids that are healthy, their weight for length Z-score is 0.37, whereas the kids with CHD is negative 0.22. So again, it started to approach significant that the kids were just a little bit lighter, less in terms of their weight for length Z-score.
And we have their single ventricle and biventricle. The single ventricle is the hypoplastic left heart, and the biventricle is everything else?
Yes.
So you'd actually...
Oh, no. Let me go back here. So the cardiologist on this, Brad Marino, he was the one that coded all of this. So single ventricle is hypoplastic. This was determined by the surgeon at the end of the surgery, what he considered that kid in terms of the functionality of their heart and the anatomy. So Brad Marino, or the physician on this study, this is who. So we've got hypoplastic valvular pulmonary atresia, double inlet left ventricle, and left transposition of the great arteries. Those kids fell into that category, and everybody else fell into this one.
So the single ventricle, they should be sicker.
Yes.
So you're probably underpowered, but you should.
We are underpowered.
Right.
So we did test for differences here, but the problem is exactly here I've got 2. I've got 2, and so I just can't do anything with that, and felt uncomfortable doing anything with that. But if you look They have a negative, it's basically negative 0.97. So their Z-scores are looking a little bit lower.
But then you had one other slide with.
This is 3 months, and then here we are out at 12 months. So in this one, it's opposite. So negative 0.71 and.
So that's what I noticed. I was thinking that looked backwards too.
I feel like we're just so underpowered. I get nervous, and Mia Pappas will tell you. She always says to me, anything less than 10, I don't want to hear about stats. And she's, in some ways she's right, because 1 or 2 kids can really skew what you're seeing. So what we did want to see too was, so we measured total energy expenditure by doubly labeled water, and we wanted to determine if those differ between healthy kids and kids with congenital heart defect or congenital heart disease. When you do that, you have to account for fat-free mass. So we did that, and after we adjusted for fat-free mass, basically the total energy expenditure of infants with CHD was 36 calories per day higher, but that difference was not statistically significant. And we saw the same thing again at 12 months. Their TEE, their total energy expenditure, is about 30 calories per day higher, but statistically it didn't reach significance. So what that tells us is that TEE in these kids is not what we thought. Their growth failure is not due to this really high total energy expenditure. There's no significant difference in what they're burning compared to these healthy controls, even after you adjust for weight using fat-free mass. And so what it really tells us is that their growth failure is likely due to insufficient intake. And when you start to dig into the literature, you'll see that these kids, when they're in the hospital, despite everybody's best efforts, tube feeds or feedings are turned off due to medical procedures that need to be done. They need to go back into surgery. They're held because they have regurgitation, and they have this host of complex medical issues going on that cause the feeds to be held. And so some hospitals have documented that these kids are only getting 40% of their caloric goals daily when they're in the hospital because all of these other things that are going on. So they're not failing to grow because they're burning too many calories. Doubly labeled water told us they're not burning that much more. It's not that big of a signal. Really, the growth failure that we're seeing is because they just have this insufficient intake. A lot of them tucker out when they're feeding. It's just tough to get the volume into them. So that is all the questions I have. Thank you for staying with me for that long. And I'm glad to see you.
Yeah, so this is wonderful. I could ask questions all day. But I'll start with one. And that relates to the common observation that kids with congenital heart disease have other developmental abnormalities and difficulties in school and so forth. And I just wonder if you think that could be related to early childhood nutrition.
I do think some of it could be, absolutely. So we know that, our brain is plastic, right? We're one of the only animal species that continues to develop their brain even after birth. Some animal species are born with it fully developed. So we definitely continue to develop our brain for 2 years at least, right? So yeah, I do think that early life nutrition can absolutely have an effect. We're seeing it in many other areas, right? You grow too rapidly, you're at greater risk for overweight. Same thing, if you grow too slowly, if you're not getting the nutrients that you need early in life, it definitely can affect, I think, your neurodevelopmental outcomes. In this study, we purposely had children that had the heart defect and no other anomalies, no other genetic anomalies or anything else that we knew about. So we tried to get the healthiest kids with congenital heart disease in that study. But yes, I definitely think it can play a role. Because that means they're not getting their essential fatty acids. There's tons of things that go into brain development that they might not be getting early on.
I was very impressed, in fact, by all the enrollment that you did for your randomized clinical trial. You enrolled 144 patients.
Yes, but it's taken a while. So I will say it's been 2 years of enrollment. So, and part of that is those subject visits. So I was the one that kind of did the projected. We enroll 6 this month and 6 next month. You start adding up the number of visits, and so we set a goal for 6 a month. But by 12 months you're up to 72 visits. It's exhausting. So yeah, we were able to do it, and that's also credit to Dr. Manella, who's been in Philadelphia recruiting subjects for years. So she's got great relations with hospitals in Philadelphia. The WIC program in Philadelphia helps out. She was the one that told me about Craigslist. I'm like, really? Really? You did? She's like, yep. You just put infant feeding study, and she's like, you'd be surprised the number of people that will call. And so,
do you pay the subjects?
We do pay the subjects. We pay them a lot for that study, and it's not coercive. Everything is approved by the University of Pennsylvania IRB, but that first subject study visit, when they enroll, they're going through all the informed consent. We're telling them all about the bottles they've got to take home. You're collecting stool. Now we're going to take you to CHOP for an REE, and we're going to dose you. We've got to get a pre-dose urine sample, and then we got to get them after. So moms are doing a lot. So they get compensated sometimes $200 for the initial study visit, $100 for when they're at home collecting. I mean, they basically get us a diaper. We get urine in these special study diapers that we hand make. And so basically we tell mom, put this on and leave it on for about 3 to 4 hours. We take a regular diaper, we line it with plastic wrap because we don't want the urine going in the diaper. Once it goes in that gel foam, I can't get it out. And that water's expensive, so I want the urine out of that diaper. So we line it with a plastic wrap, and then we put a cloth diaper in there. And we ask moms to leave the diaper on until it's saturated. And some moms can't take it. They're like, oh, she's crying. And we're like, please leave it on. So we ask them to leave it on for about 2 to 3 hours. All mom has to do when she's done is fold it up, and we give them a plastic baggie, and they need to freeze it because those isotopes will evaporate if it gets left at room temperature. So we give moms this little freezer bag that you can't see in, and we say for 7 days, just each morning you put that study diaper on, leave it on for 2 hours, close it up, and put it in your freezer bag. They're collecting every stool sample for 3 days. God bless these moms. Some moms can't do it, and I get it. I will say that we're going to have missing data points for that study, and it's worse in the beginning. Anybody that's had a baby, your first 2-3 weeks home with them, you're like, what? Especially if it's your first child. But they got better, as the study went on. Definitely. The bottles ended up being the easiest thing because they just go home with 36 of them, feed what you want, and throw it in that bag. I will say they smell when they come back, and we have a sterilization process so that, we make sure that they're really clean before they go back out again. So yes, our group in Philadelphia is also very excited that we have enrolled our last subject. And my lab here is like 56 more stool samples to go. So they've started a countdown also. My mantra is if you have a bodily fluid, I will collect it and take it. And it seems to be playing out. Yes.
What's your preferred formula?
Oh, a preferred formula? Oh gosh.
You presented a few different ones up there.
I don't necessarily have, to be perfectly honest. I can't say that one brand is better than the other. So I did work for an infant formula company for 4 years. What I will say is I was on the R&D side, and I'm grateful that the companies, they would give me money to do studies. So one of the studies I did was, can we lower the total protein in the formula and have infants still grow like they should? So we were able to get the formula down to 12 grams of protein per liter, and they still grew. So I was grateful that they were still interested in improving the product. I did not like doing research for profit. It just was not, it's just not who I am. And so I struggled with that aspect of it. But in terms of being a scientist there, they really, as long as I designed a good study, they let us ask good scientific questions. We did a study where we looked at carotenoids, so like lutein, zeaxanthin, some of those things that we get in fruits and vegetables. Those aren't in infant formulas, but they're in breast milk, because if I eat them, it ends up in my milk. So we were interested in looking at, well, what's a normal amount of lutein in breast milk? And should we be putting that in infant formula? Would it help with development if we did it? So we got to ask great questions. I just didn't like what happened after I did my great questions in my studies. It kind of became commercial. So the infant formula companies are trying to improve the product. If you're a scientist there, you're trying to improve it because you want what's best for the baby. You want any baby that can't be breastfed to get something that's as close as possible to human milk as you can make it. If you're on the marketing side of it, you want to know, well, how much does it cost to make that improvement, and how can I sell that improvement? So I didn't like that end. I worked with nice people. I didn't like that side. I liked the science side of it. So infant formulas are changing so often now. That's what it's dizzying. So I don't have a favorite formula at all. I would like to see whether this protein hydrolysate formula, I don't think we should give it to everybody. It's more expensive to make a protein hydrolysate formula. But maybe if you're an infant at greater risk for obesity, maybe you shouldn't be on a cow's milk-based formula, and you should be on this protein hydrolysate formula. Maybe that could protect you against too much weight gain as an infant. Not all babies will grow rapidly, right? 10% of babies have high weight for length. So I don't have a favorite formula, whatever the infant tolerates, and we have a lot more work to do to know if that protein hydrolysate formula should be given to certain babies for weight issues. Yes.
Has there been any studies, like if let's say the baby starts increasing the growth rate, would you then switch them?
We People are nervous to do that, I have to be honest. So I don't know that we have a lot of data yet to say this. At what point do we say your growth is too rapid? Do we do that at 2 months? Do we do it at 4 months or 6 months? I just don't think we have the data to make an evidence-based decision about clinical care. I think that we would need to do a study to get the evidence to say, okay, if you've gained, so normal rates of weight gain are 25 to 30 grams a day, right, in the first 6 months of life. If you have a kid that's gaining 60, you know what I mean, is that a kid? But I think we need evidence. We've got theories and we've got probabilities, but I think we need the evidence to make that type of a clinical care decision.
Great. Well,
All
thank
right.
you so much.
Thank you for having me.